just wanted to check the slide. If our K is 0, Gibbs free energy is 0. If Gibbs free energy is 0, the cell potential has to be 0. Okay? See those relationships? So you should be able to work with those three. Chapters 19 and 20 are kind of fun because they seem very different in terms of their concepts, but they actually tie in really well together. So you're thinking a lot about Gibbs free energy when you're working with electrochemistry, because we're going to take the electrical potential that we generate in galvanic cells and put them to work, which is going to be our free energy. When you're working at non-standard conditions, so in that case you're looking for E cell, no not sign. Okay, this is your standard condition, E cell, E not cell. And if it's not for a galvanic cell or a voltaic cell, you might just be looking for the potential. It's a more general way of looking at this. What else? So another clue that you're looking for, you're going to use the Nernst equation. Okay, you got your E cell, non-standard, and you're given concentrations of species. All right. If you see all that, that's how you're going to know you need to use your Nernst equation. Okay, just sort of to summarize a few of the things with the Nernst equation. When you calculate the cell potential, that is the maximum potential that is attainable. Once the electrons start flowing in a galvanic cell or a voltaic cell, the concentrations change. So you're converting an ion to a solid, and solid to an ion. So the concentrations in the half cells begin to change, which means that Q in the Nernst equation is going to change. So again, E cell equals E naught cell minus 0.0592 over N log of Q. All right, so when the concentrations are changing, Q is changing, and that's going to change your cell potential. Your cell will produce energy until it reaches equilibrium, and that's when Q is equal to K. Okay. So when Q is equal to K, the Gibbs free energy is equal to 0. And so your cell potential is equal to 0. Let's see. So if we go back to that. Okay. There's another type of galvanic cell or voltaic cell. It's a special type. It's called a concentration cell. And excuse me. These are kind of interesting because they use the same half reaction in the two different cells. Okay, so in this figure, both cells are taking nickel. I guess I'm writing this as an oxidation, forming nickel 2+ and 2 electrons. So in one half cell you have the oxidation, and the other half cell you have the reduction. But it's the same sort of thing happening. The only difference is that the concentration is much higher in one of the cells than the other. And basically what happens is that the electromotive force, or the potential, is dependent on concentration. And we know that based on the Nernst equation. Okay, so we don't actually have to have two different reactions taking place in our half cells. We just have a large difference in concentration. So what will happen in a concentration cell is that we'll get a reaction occurring until eventually equilibrium is reached, and equilibrium is reached when the concentrations are the same. So in this figure we're showing concentrations of the nickel ion. So they're both 0.5 molar, whereas when we started, on the right-hand side, the nickel ion concentration was 1 molar on the right, and on the left it was 1 times 10 to the minus 3 molar. So now they've sort of equalized both out to about 0.5 molar. Okay. It's kind of fun. You can kind of think of this as parallel with osmosis, where you want to sort of equalize concentrations per se. That's sort of what's happening here, but it's changing that. But it's the fact that the concentrations are so different that results in a large difference in potential, which means we can actually use that, capture that flow of electrons for energy. Z when we reach equilibrium, okay? Brutal. Okay, so let's calculate the standard cell potential for a concentration cell. So if you remember, standard cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. Okay, so I'll let you guys calculate this real quick. Let me know what you get. Give you a few seconds. Talk to your neighbors. So you have the reduction potential. Yeah. All right, what do you get? So at the cathode, we're going to have minus 0.28 volts. We'll have minus 0.28 volts at the anode. So you end up with 0 volts. So just given our standard reduction potential, so what this is telling you is that if you had 1 mole per liter in each of the half cells, this wouldn't work. This wouldn't do anything. And that's basically like, but why does this actually work? So we actually need to use the non-standard formula. So we're at non-standard conditions. We need to look at the Nernst equation to see why we actually get a potential difference. We get an electromotive force for our concentration cell. So now I'll let you calculate the cell potential non-standard conditions using the Nernst equation, and I'll give you a minute to do that. How do you write an overall reaction for this? This is a little confusing. You need to know that oxidation will occur in the cell with the more dilute solution. And reduction in the more concentrated solution. Okay. That's going to help you write your overall reaction. All right. You need to write the overall reaction in order to figure out which is your products, which is your reactants for use in Q in the Nernst equation. So at the anode, we're going to have our nickel solid forming nickel 2 plus ion and 2 electrons. And at the cathode, we'll have nickel 2 plus 2 electrons forming nickel solid. The 2 electrons cancel. And actually, I need to be more specific here. In our anode, we're going to have aqueous but dilute. In the cathode side, we'll have aqueous but concentrated. So we can't actually cancel out our ionic nickel. Okay? The solid does cancel out. So overall, we're going to have nickel 2 plus aqueous concentrated forming nickel 2 plus aqueous in the dilute cell. So basically we're going from a concentrated cell to forming to the more dilute cell. And so you take your more concentrated side, that's going to go on and react to concentrate, essentially more concentrate the dilute cell. You know, see what I'm saying? They have to equalize. So now that you have an overall expression, overall reaction, now it's a little bit easier to write out your Nernst equation and figure this out. Q in this case is going to be equal to the nickel concentration for the dilute cell divided by the nickel concentration for the concentrated cell. Okay. Now you can make a Nernst equation. How many electrons are transferred? 2. We previously calculated our standard cell potential to be 0 volts. We have 2 electrons, and for Q we're going to have 1 times 10 to the minus 3 molar divided by 1 molar. I apologize, guys. It was terrible. And we'll end up with a cell potential of 0.0888 volts. So relatively small, but if you were to line up a large number of concentration cells and link them all together, you could end up with a relatively large cell potential. Questions on this? Yeah.
So how do you know which side is going to be the dilute and which side is going to be the concentrated? Is it just always keep the Q less visible there?
So I think of it more as you're always going to have oxidation in the more dilute solution and reduction in the more concentrated solution.
Okay.
And so that'll allow you to set up your half reactions and then write the overall. Other questions? Yes?
Why do we use E cell instead of
So for the Nernst equation, you use the cell potential. Nernst equation is just for cell potential. Reduction potentials come into play when you're calculating the standard cell potential. What else? the end of that slide deck.